So in this chapter, we're going to talk about rotation. So far, we've talked a lot about linear motion, and linear motion is when things move along a straight line. And that can be in the X, Y, Z, or some combination of those directions. But rotational motion, we've talked a little bit about circular motion. We're going to review that a bit. But rotational motion is anytime something turns around an axis, okay? So here, an example of rotational motion would be a wrench turning a nut and bolt set. That is a rigid body, and what we mean by rigid body is anything that's not squishy and also something that's not considered a point, because in almost all the previous things that we've used, we've considered our objects to be a point, which is mathematically something that doesn't really have any dimensions. It's like it's like a one-dimensional object. So now we're coming into 2 and 3 dimensions, which is more like what happens in the real world, but the motion of a point still works for sort of the center of mass motion for things, and we'll talk about what that means later. But in the previous chapter, we discussed center of mass, so the center of mass moves like the point, but then things can rotate around it. There's rolling, there's lots of rotational motions that we can address. So just to give you an overview of what we're going to be talking about, we're going to review sort of the first 3 sections are sort of review. So we'll talk about angular velocity and acceleration and sort of define the coordinate systems we use. We'll talk about constant angular acceleration and review some circular motion. And we'll talk about the relationship between linear and angular kinematics. Then in this 9.4, we talk about energy and rotational motion, which introduces something called moment of inertia and rotational kinetic energy, which are both pretty important. We've talked a lot about energy and about inertia, which comes from mass, but when things rotate, not only does the mass matter, the shape also matters. And then we'll talk about parallel axis theorem, which is a nice shortcut. Then we'll get into a deep dive of moment of inertia, where we'll talk about how to use integrals to find the moment of inertia of any object. So starting with angular velocity and acceleration, just as a review, remember, if things are rotating, we have to change our little dynamics of how we define our coordinate system. So angular position is described by an angle. That would be in radians or degrees. It's not in meters like our other directions, and it really it relates to the distance traveled by the arc length, but you still have to multiply that by a radius. So angular position is a little bit different from linear position. It's not necessarily like X, Y, and Z. It's got a little bit of a different thing, and that way anywhere you are on a rotating object, you can have the same angular velocity and angular acceleration, even if you're close to the center or far away from the center. As you may know from being on spinning objects as a person, if you're close to the center, you're not moving as fast as if you're out by the edge. So this is independent of that. So your linear velocity varies by radius, your angular velocity doesn't, okay? Angular velocity as a vector is really interesting, because angular velocity as a vector has a direction, but the way we figure out the direction is we curl our fingers in the direction of motion, and the vector points in the place of your thumb. This is called the right-hand rule. So you curl the fingers in the direction of rotation. So if something's rotating this way, we curl our fingers, and then it has an angular velocity vector that points this way. So if this is like a disk, right, and it's spinning, the angular velocity vector is perpendicular to the disk. And of course, this works with only the right hand. There's a really good demonstration of this that you can see, and we'll I think do later. But you can see how conservation of angular momentum works as a vector by having gyroscopic motion, which is like if you spin a wheel and you stand on a platform. When you turn the wheel, something sort of unexpected happens. So we'll leave that as a preview for later. The more formal mathematical way to describe this right-hand rule is with a cross product. And remember, a cross product is something we've learned about in math, but we're going to apply it a lot with rotation, especially with torque, and then it's going to come up again in the second semester of physics when we talk about electric and magnetic fields. So the cross product is A cross B, and like mathematically what that is just the simple way of thinking of it is AB sine theta, but really the cross product is a multiplication of 2 vectors, also determined by the right-hand rule, where the resultant vector is going to, well, the result is also a vector, and it's going to be perpendicular to the plane created by the original two vectors. So this is the right-hand rule, and you always do first vector, second vector, right? First vector, second vector, first vector, second vector, and this is your result. So you point your finger, this would be in the direction of A, right? This would be in the direction of B, and this would be your A cross B. It's very important to do it with your right hand because, as you can see, if there's a plane, you can either go up or down, and the right-hand rule tells you which one is the correct one. So just as a side note, if vectors are parallel, because it's a sine, the sine of 0 is going to give you 0, so parallel vectors in a cross product gives you nothing. If you have an angle between 0 and 90, that's going to be smaller than A times B, and then if they're perpendicular to each other, you end up with just AB, because remember the sine of 90 is 1, okay? So, going on to angular acceleration, just as a reminder, for translational motion, we have these kinematics equations. They come from the definition of acceleration, and if you have a constant acceleration, you can work backwards and get these three equations. We did that in the beginning of the semester. Dynamics is just force equals mass times acceleration. So if you have if you have force that results in acceleration, that's described by the motion of kinematics. And then we've also talked about momentum and energy conservation. We've talked about all these things in terms of linear and some circular motion, but now we're going to talk about them in terms of rotation of things that aren't just points. So rotational motion has very similar setups. You can see that the kinematics equations are essentially the same. We've just changed the variables. And if you divide through all of these equations by r, actually multiply through by r, then you're going to end up with the same kinematics equations we had before, because these are the relationships here between the linear or tangential acceleration and angular acceleration, tangential velocity and angular velocity. So for dynamics and momentum and energy conservation, we haven't really seen how those are related, and so we're going to get into that in the next few chapters. How do we relate linear and angular kinematics? Well, just some housekeeping. Remember, to go back and forth between linear and angular, you just need these conversions, because remember, arc length is sort of the circular version of distance, and then you have tangential velocity, which you can get from angular velocity, right? That's what this is. You have tangential acceleration, which you can get from angular acceleration. So you can go back and forth from the linear values to the angular values by just multiplying or dividing by the radius. Okay, so that brings us to energy.